the computer tends to work to the center, unless, of course, the architect tells you otherwise. And in this case, the architect did have them move these members over, but this member coming in here, boy, we ran that thing right into the centroid of that column. Think of how much nicer it would have been if we'd have moved that thing over and put it on the center of the flange. You'd have reduced the weak axis eccentricity of that column, and you'd have made that connection much, much nicer. But I know that's not the way you normally snap the lines in the computer, right, when you're building your model. But that's something to keep in mind. Another thing that the computer doesn't do is, this is again, I think like a 6-story building. This is a little piece out here. It's only 12 foot long. It's a 1219 out here, and there's actually a column out here. There's not much floor load out here, and the wall system is relatively light. And so Ram Steel said that works fine. And that's what the detail looks like. But let's start to think about this, you know. We show, this is a gauge edge form on here, and we show you have to have at least 2 inches minimum bearing on the gauge edge form. Now that's a 4-inch flange to start with. All right, so now we're to the center of the flange with the gauge edge form. Now you've got deck on here, and the deck's got to have at least 1 3/4 inches, ideally 2 inches on there. So that goes almost to the center line. Now you've got a stud on there, which according to AWS has to be in the center. Getting pretty crowded on that beam right now, right? I mean, maybe you could go out there and burn away part of this and burn away part of this and get that stud on there where you need to. But now keep in mind is that this is actually erected to an AISC frame tolerance, which says that that member can what? Be in or out 1 inch or more than that. And yet this is being erected to adjustable tolerances. It has to be plus or minus 3/8 of an inch. So what happens if this beam's over 1 inch or this way 1 inch? You know, there's just not enough room on these 4-inch flanges at the perimeter if you're trying to do all this stuff at the perimeter. You know, you have to give some thought to constructability. Talked about cantilevers. This is another case of cantilevers. This is the job we were doing. This is, again, a 2-story building. This is the 2nd story, and relatively high floor to floor. And this is a, you know, this is a fairly long cantilever. I think this is somewhere in the neighborhood of 15 foot or more on the cantilever. And this is a CJP welded detail and everything on there. If you look at the detail that we had, the only way you can erect this thing is you got to shore this thing out here, and then you got to CJP weld this and CJP weld this. And there's just a lot of work and a lot of difficulty in doing this. We looked at this thing and we said, you know, first of all, every other one of these columns drops off at this level because the roof columns have twice the spacing. So that's no brainer. If this one drops off, we're going to run this over the top. You know, that's easy. But then we started looking at these and we said, you know, we'd still be better off running these things over the top because now you don't have to shore that cantilever. And yes, we have to build this member out and we have to put continuity plates in and probably widen the flange out and do a lot of work. But, you know, we can do that for about the same fabrication we got in here, and now we've eliminated all that field welding and all that shoring. And in this particular case, the erector was our customer, the general contractor, and he loved us for it, you know. But we also came up with a better, safer solution. So on long cantilevers, see if you can't run the cantilevers through. You know, that's a safe way of doing it. You have to keep in mind that there is a you know, there are different conditions, and sometimes it doesn't make sense. We were doing a hospital condition again, big hospital for one of our local firms up there, and they had done a big hospital out east not too much before this, where, again, they found that the cantilevers on this hospital had all been erected, and the erector had not completed the moment connections on the cantilevers. And they hadn't lost anything. They caught it in time. So they went out, but they were thinking about, gee, how terrible this could have been. So they established their in-house safety rules that they were going to run the beams through and stack the columns so they wouldn't have this problem. I think we probably did the next job, and they said, all right, we're going to run the beams through and stack the columns. The problem is that we had, I think, a 2468 beam and a 14-inch 311 column. You know, it doesn't make sense in that case to do it. You know, we could have easily done an end plate on the thing and bolted it to the column or made it a bolted connection. So you've got to keep in mind which ballpark you're in. Now, you never make changes in your jobs. I know your customers don't make changes, but we do screw up every now and then, and we miscut something, or we can't get the material we need and we have to splice something. And so you shouldn't, I mean, as a general rule, the fabricator shouldn't come out and be taking a bunch of stuff out of the scrap pile and welding it together. But there are going to be cases where he's going to have to do some splicing to make the members work. And this is just a standard shop splice detail. AWSD 1.1 says is if you're going to splice a member with a groove weld, it has to be a CJP weld. You can't use a partial penetration weld. I think part of that is because once you do it, you may not know later on, and so they're saying splice it for the full strength of the member. And so this is just a typical detail that we use in splicing. And so if a fabricator comes out and says he has to splice because he's either misordered or miscut or because there's a change in the job, it's not the end of the world. Member selection guidelines, we'll sort of summarize. We're saying use a W12 minimum depth for floor framing. A W12 will allow you to get a 3-row connection in, and it'd be reasonable stiffness. Try to avoid the W8s. It's hard, to even get 2 rows in there decently and develop some capacity, particularly if you have to cope them. With these light 12-inch 14s and that, it works. Now, if you've got a girder that's got a big wide flange and thick flange, maybe even move that to a 14-inch member so that you can do that cope and not have to reinforce it, Avoid beams with 4-inch flanges like we just talked about at Spandrel beams, where you have to put a lot of stuff on there, where you got to do an adjustable edge for them, you got to get studs on it, all the other stuff. Where you've got bolted flange connections, where you want to stack a small post on top of it or something like that. Very, very hard to put a pair of 13/16 holes in a 4-inch flange. You don't have a hell of a lot left. I mean, we can't even run those down our punch lines. We have to go and drill them by hand typically in order to get the holes in. So if you're going to try to do hangers off these things where they're going to be bolted like that, I mean, you can adjust and use plates or something else, but if you're going to put a post on top of it, kick it up to I don't know what, 1222 or something like that, something else that's got a little flange on it. And if you got joists from both sides, you need more than 4 inches to land your joist on. Composite beams, we're saying limit deflections to avoid large cambers. I believe the AISC Code of Standard Practice makes some recommendations on maximum cambers for various beams. It's pretty generous, though. Try to use maybe more like 50% composite when you're designing these beams. We find that people that try to go to 100% composite, it gets very, very difficult to get the number of studs in that you need. The other thing is that you really need to look at the 2005 spec to look at stud values now. There's some new different formulas for stud capacity. It's based on the number of studs in the corrugation and other things, and so it's probably going to reduce the values. Ideally, you'd like to design your percent of composite, so if you're using a deck that has like a 1-foot module where you've got a corrugation every foot, you'd like to have a stud every 1 stud per corrugation in that range. On the girders, of course, that's not an issue because you can break cover and put studs in there as you want them. If possible, consider the fact that if you've got beams that are running parallel to their deck ribs and you're starting to call for studs in there, that may be a real problem because, first of all, you got to make sure the beam ends up under a corrugation, under a rib, otherwise you won't be able to get it. Most ribs have a little stiffening rib down the middle, so that might create a problem, so you might have to blow away the deck in order to do it. There's just other considerations. So if you could design, if they're at an opening, it's not a real problem because you got to break cover anyway for the opening, and you put a closure in or something like that. But if it's an intermediate filler beam or something like that, consider making it strong enough so you don't have to add a stud to it or something. Or at least be aware of the fact that when you see shop drawings that they have to figure out a way to get the stud in. Show reactions on framing plans. Again, like I talked about, more economical, helps avoid errors and reduces the RFIs. Use standard AISC details. Hopefully we're going to have some more standards in the future. We're saying double angle, bolted or bolted welded for the heavier connections, and in our case for column connections. There are other places in the country, you know, out in the West Coast, they like to use, the erectors really love single plate connections. And with the capacity you've got now in single plate connections under the new design rules, you probably could go to single plate connections on a lot of columns. It's difficult to go in the web, so, because you still have that problem having to extend the plate out in order to access the holes. So use single angle or single plate for beam to beam and single plate for skewed. Again, single-sided connections are very economical. They're safe. It's really the way to go for infill connections unless you have some very heavy loads. If you've got skewed connections and you can't handle it with a single plate connection, then use an end plate welded to the web only for shear. That's a nice way. I recommend avoiding bent angles. The only time I would use a bent angle type detail, there's a couple of single ones you could use for extreme skews, but generally I would use them only if I were going to a skewed connection to concrete and I needed the type of adjustment that I could get with those angles where I could move the beam back and forth and then weld it on the condition. But other than that, other than those skewed connections to concrete where I need that adjustment, I would avoid bent angles. Show special connections, you know, like we talked about. Moment connections, we're saying provide actual moment envelope. Design considerations, we're saying end plates may be limited by bolts or column flange bending capacity, but end plates are becoming more and more popular. There are a whole series of pre-qualified end plates for seismic connections now, and I would highly recommend that for if you've got relatively medium to light loads for seismic type connections, and end plates would be a good way to go. CJP wells are a no-brainer for moment connections, but they're generally more expensive, but there may be cases where you need to do it. Top and bottom plates like Jim showed there are an option if less than MP is required, but it's usually hard to get MP. One of the things I might mention, again, I don't know how familiar you people are with the 2005 spec, but one of the larger changes that went through in the 2005 spec is the effective flange area with bolts and for bending. You know, we had a requirement before for if the bolt holes exceeded a certain amount that you could no longer use the plastic section modulus. You had to use the elastic section modulus and reduce the capacity. And it used to be that if you had bolt holes that exceeded like 8% in 50 KSI material, that you had to start taking a reduction, and it was a pretty substantial reduction. The new spec actually is somewhere in the neighborhood of 25 to 30% reduction. Holes can be that large a percentage of the flanges before you have to start reducing the strength. You can use the plastic section modulus up to that level. So that's a nice increase in strength available for bolt and moment connections. Size column to avoid reinforcement. Again, put a plug in for the AISC website. There is a steel tools program on the AISC website that allow you to evaluate whether you're going to need reinforcement. It'll even go so far as to give you how many pounds per foot you can add to that column before reinforcement becomes economical, you know. So it's a little program Charlie Carter put together, and see the AIC website. I would also comment that the 2005 spec has changed the requirement for continuity plates for tension. It used to be that if we had to put a continuity plate in under the LRFD specification, that we had to weld the continuity plate to the flange to develop the full strength of the plate. The 2005 spec says no, we're going back to what ASD used to do, and that is our connection of that plate to the flange only has to be for what additional strength the flange needs to support the design load. That's going to be a savings if you're starting to use heavier plates, particularly if you've got plates for weak axis and strong axis. So that's a nice little savings based on some research done at the University of Minnesota by Professor Dexter and Hajar. Unfortunately, we lost Dr. Hajard at the University of Illinois. Cantilevers, actual moment and shear forces. Indicate if camber is required, again, not for continuous ones, but for other types of welded cantilevers, you might want to require some sort of a raised condition to account for camber. Use end plate connections where possible for ease and erection. That's for safety. Shop weld short cantilevers. And consider making the beams continuous and stacking columns on long cantilevers. Bracing connections show all forces and complete load path, provide equilibrium condition at the joint, or provide actual transfer forces. I mean, we've seen brace details. Quite often when we see a brace elevation, all we're given is the force in the diagonal, and you have no idea how that force gets into that diagonal. Does it all come in through the horizontal beam in that one bay? Is there a transfer force through the column? I mean, I've seen conditions where we have a brace force in that vent, and there's no way you could ever get that type of force into that brace because the capacity of the roof diaphragm is nowhere near adequate to develop that type of force. But somewhere they had forces and they just calculated the brace, never worked the load path out. Forces should include all drag strut forces and diaphragm connection forces like I talked about. And consider modifying work points for extreme connection geometry. In other words, if you've got a brace that's relatively flat, you know, coming in, and you put that work point down at the center of that girder, you know, you're going to have a gusset plate that's going to be very elongated, may not even connect to the column, you know, and depending on the condition of the connection, it may get to be huge. There's no reason that you can't maybe work that, change that work point to the top flange and work to that point. Yes, it's going to put a little moment into your girder, but if you've got a big heavy girder there anyway, that type of eccentricity you're going to have from that brace is going to be relatively small. And so, but it's going to make the connection a lot nicer. I mean, I talk about the fact that we've been brought up in engineering to worship what I call the great God of concentricity. All the forces have to resolve at a point. I mean, you know, if they all meet at a point, then we don't have any moments, right? You know, all we got is axial forces. But what happens is the connections are made out here, so we're throwing all these eccentricities and moments into our connection material. And wouldn't it be better to make your connections so your connections were symmetrical and all you had was shear forces there, and take some moments into your members? Your members are easier to take it. So keep that in mind. It may make a little more work in modeling, but will pay off in the long run for details. Allow oversized holes in field welding were required for constructability. Again, we recommend the AISC website, the AISC Manual of Steel Construction. I think the 13th edition is really a great, I didn't really have anything to do with the 13th edition, but I'm impressed with it. I'm sure there's going to be problems. I can criticize certain items, but overall it's a prodigious piece of work. Acknowledgements, we've got AISC Solution Center, Volcraft, and some joist details. Our good friend Tom Farrell from Farrell Engineering, who helped us with some of these details, and Gantrex Corporation. Any other questions? Yes?
What could or should you request in terms of calculations from the fabricator?
What's this from what good is?
What should we or could we request in terms of calculations?
I would say that there's no reason, I mean, as far as I'm concerned, calculations, you got this? Oh, I'm sorry, okay. The question is what should we expect in the way of calculations from the fabricator? If the fabricator is going to be responsible for design of connections, then of course they're going to have to supply complete calculations with a seal on them. The state of Illinois, I would say that if you're going to review them and accept them anyway, we wouldn't necessarily have to have an Illinois SE, but most people would want an Illinois SE on them. You know, we're going to design them for basically the loads that you give us and stuff like that. We've done it both ways. We've had firms that say, we're still going to be responsible, but you know, you can select the connections, you give us calculations showing how you think the load paths go, and we will review them and make our own design decisions, you know. And that way, because quite frankly, even if we submit stamped calculations, if there's a problem, we're all going to be involved. If we don't submit stamped calculations, we're all going to be involved. Yes?
Typically, is an engineer the one doing the detailing, or is it who's doing the detailing?
The details are being done, and nowadays, the vast majority of them are being done in India, China, South Korea, you know. That's where the details are being drawn, typically. There are some being drawn in the U.S. But what happens is that we would either, with our own staff, who are registered people, or we would hire a registered firm to do connection designs. And we would submit these details along with connection calculations, ideally in advance, so that you could review them and say, yes, this is acceptable, and then our detailer could take off with them and put them on. Now, the next question is that how do you approve shop drawings then? I mean, should the connection designer of record review the shop drawings? You can't really, they can't seal the shop drawings because the shop drawings are not being prepared under their supervision. They can review them and approve them as you would, I guess. And so that's another issue that can be done. Otherwise, maybe if you're going to review them and approve them and you've got all their calculations, maybe that's all you need to do. It depends on the complexity of the job and what you're all going to do. Yes?
Is that not the problem of equilibrium in a joint?
Yes.
And enveloping the stuff. I'm just wondering, what solutions can we do about that? I've run into that a lot. I've got dozens of typical connections with dozens of load happening. And there's no way I have enough budget to resolve all this in one second.
You're talking about equilibrium conditions in a joint, and how do you show equilibrium conditions in a joint? Now, are you talking about primarily about an axial loaded condition where you got a brace force or a truss force?
Yeah, and possibly some moments in there as well.
Okay. Hopefully moments shouldn't be that difficult. I mean, you should be able to go through on a moment and pick out the maximum positive and maximum negative moment, and that should be adequate on a moment joint, you know. And that shouldn't be that hard to do. But axial load conditions get to be more, particularly when you have more members into a joint. And the rationale is that if you had 5 members in a joint, you would have to have probably at least 2 or more load conditions for each member. You know, so you'd probably have to have 10 load conditions to give all of the maximum forces, and you wouldn't really be given an equilibrium condition, but you would know that when this maximum force occurs, this is what happens. And you know, when this maximum force over here occurs, this is what happens. So you could design the joint that way. That's one of the problems we're coming up with, and hopefully we'll have some sort of a paper discussing how to do this. I know one of the speakers later in the week, Larry Griffiths from Walter P. Moore, has made a proposal in our committee on how to show this and that. You can get by showing the maximum forces if you can show what the pass-through forces are, but there's a lot of confusion about what really is a pass-through force, you know. And we haven't gotten real, because we have, in that committee, we have a couple of connection designers, and they don't always agree with what they need to design the connection either. Yes, I don't know if I've answered your question, but it is a problem. Yes, you get a lot of different load cases. No, you got it. Well, the question is if the governing code is the IBC 2000, right? Can you use the 2005 AISC specification? I would say technically, by the code, you probably have to use the 89 or the 96 or whatever it is. But But I don't think any building official, if you went to them and said, hey, we want to use the 2005, would have any problem with using the 2005. But it's something I think you'd have to at least pass by the local official, particularly when you can point it out that the 2006 IBC uses this code. And you want to go to, just tell them you want to use the provisions of the 2006 in regard to steel. Maybe that would be easier. Yes?
Just one air talk was we recently been working on information working with Federal Engineering. We've got a process where we've had Federal Engineering provide us with capacity values for a set of pre-established connections. And as a result of working through that process, we now have a booklet or encyclopedia of capacity values for a set of pre-established connection detail arrangements. Our engineers in-house look at those and determine whether the connection is going to be okay or not, and ask for supplementary calculations to be prepared if they come across a situation that hasn't yet been covered off in our encyclopedia. Again, it's far from ideal, but as you've explained, it's a very elaborate process no matter how you want to approach it. There is no simple way to do it correctly.
Now, you're a fabricator?
No, I'm an engineer with Fluor.
Okay. Tom Farrell of Farrell Engineering, and Bill Thornton from Survey, and myself were the three people that were involved trying to do just what you're talking about. And we do that at Lejeune also. We have a series of stock shear connections. Farrell has it, Survey has it, and we have it, and probably other, we have all these stock connections. And if we get a job, and we have the loads on it, the first thing we do before we do anything else is we send those standards in, and that's going to cover the vast majority of shear connections. What we're trying to say, and what even Farrell agrees, I think Cindy Duncan or somebody questioned it, Tom Farrell, he says, well, do you want to give this up because you're charging people for it now? He says, don't worry about it. He says, there's so many other connections that take so much design time that we're not going to lose any business if we can get these standard shear connections out of the way so everybody agrees on these standard shear connections and we don't have to mess around doing RFIs and stuff on these standard shear connections. But yes, that's the idea, is that you've got it from Farrell. We'd like to have AISC produce that and make it available to the entire profession so that you could put these standards on your design drawings or pick connections if you wanted to ahead of time and indicate on your design drawings, these are the connections to use.
Yeah, we follow the process even on more complex connection details. We follow the same work process of giving the information over and getting the connection engineered up front, including complex bracing, moment connection, issues where we have axial loads, horizontal loads in two directions on a connection as opposed to simply vertical shear. We have horizontal shear as well as axial load.
Do I understand you use a firm like Farrell ahead of time so your bid documents have this information on them?
We actually hired the fabricator. I believe the contract is a cost reimbursable for the engineering effort.
Okay. I know that I was talking to, there's a firm here in Chicago that does connection design, and they were hired. The owner wanted to avoid this problem, so they went to the structural engineer of record and said, I want to have connections designed on the drawing of design documents. So they went out and hired another connection design firm to provide these. The interesting thing is that the lead engineer got all the loads, called up the engineering firm and said, are you sure these are all loads? These loads are all so light. And they said, oh my God, we gave you the actual design loads. So anyway,